Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to the first module for week 1 of this course. And I hope you have watched the overview module. And as I explained there, what we'll be doing in this course, largely, at least the first 4 weeks, would be this quantum description of devices. And as I explained, this involves starting from this Schrodinger equation, which I'll try to explain a little more in this module. That's this E psi equals H psi, to which you add this new term due to the contacts. And so for any device you want to model, and the first things you want to know is what is this H and what are these sigmas. And this week in general we'll be talking about how to write down the H. And in the coming weeks we'll be talking about different problems and how you write the sigmas, and then how you go to these NEGF equations and actually calculate quantities of interest, like current and density of states and electron density, things that can be compared with experiment. So right now then, our main objective this week is about understanding this H and where it comes from, how to write it down for materials of interest. And as I explained earlier, in the overview lecture, that the starting point is this Schrodinger equation. And what the Schrodinger equation looks like, and again, this is something, even if you're not familiar with it, you may have probably seen it here and there. It will look something like this. E, that's a constant, times psi, a function called the wave function, is equal to this minus h bar square over 2m. M is the mass of the electron. So this is a fundamental constant, these things. And this is this del squared. And in 3 dimensions, it sort of is the sum of second derivatives in x, y, and z. It's the sum of those things. That's what's called the Laplacian, acting on psi plus the potential that the electron finds itself in, this potential energy, times psi. And sometimes people kind of don't write the psi here. Instead, they would write it this way, put a parenthesis here. The understanding is that this differential operator acts on that psi. And then you can write it as E psi equals H psi, where H represents this differential operator. See? And as we'll talk about in the next module, is how you can write an equivalent matrix equation, where instead of a differential operator, you have a matrix. But that's for next module, really. Right now, I want to give you a feeling for this differential equation itself. This is the basic Schrodinger equation. Now, if you ask me where it comes from, the point is I'd say that it's not really that you can derive it as such. You'll see a lot of derivations often in the literature and various places, but I think the way I think of this is, when Schrodinger wrote this down in equation in, I believe 1925, see what gave people a lot of confidence that this has something right about it, that it's correct, is because he was able to solve this equation for an electron in a hydrogen atom. You see, in a hydrogen atom, what you have is a positive charge, this nucleus. And the electron is kind of pulled by this charge, and so the electron has to stay around it in that region. And what was experimentally known is that the electrons in a hydrogen atom have certain discrete energy levels. How did they know it? Well, experimentally they had studied the light emitted by a hydrogen atom. So when they heat up this hydrogen atom, then just like a light bulb, it would give out this light. And the frequencies of light corresponded to these differences. And from that, people had a pretty good idea of what these levels are, you see, experimentally. And what Schrodinger showed was that if you take that equation, you see, and solve it for an electron in a hydrogen atom, which means the electron, of course, sees a particular potential energy due to this one positive nucleus. So for a given positive nucleus, for a positive, like a point charge, the potential you get is something like q squared divided by 4 pi epsilon r. Because when you have a point charge, the potential around it, goes down as 1 over r, the negative sign here. So that's what U would be. And what he showed was that for a potential energy that looks like that, you can solve this equation analytically, and you can show that you only get solutions when the energy here takes on these specific values, E1, E2, E3, etc. So you wouldn't get any solutions unless E happened to have one of these values. These are what you call the eigenvalues of that differential equation. Now, and the energies he calculated matched the experimentally known numbers extremely well. And that is, of course, what immediately gave people a lot of confidence that we were on the right track. This describes what is actually happening here, or describes reality, if you will. And this is why I say that, you see, this is that science and math are kind of different. In mathematics, usually it is the way you have confidence in the correctness of something is more by the logical derivations, like Euclid's geometry. It's a great example of that. That given a set of axioms, other things follow logically from it. On the other hand, in science and engineering, most times I'd say, the reason you have confidence in something is because it describes reality very well. And that you know by looking at experiments. See? So rather than go through any derivations of this equation, what I think I'll use this module for, the rest of the time in this module for, is to give you a feeling why an equation like this leads to discrete energy levels. See, because that mapping from the math to the physical fact, you see, that isn't obvious. Looking at this equation, it's not clear why, when you solve something like this, you should get discrete energy levels. So what I'll try to explain is why that happens. Now, to get a physical feeling for this, you see, it is useful to look at something that we understand better. And that is like acoustic waves on a string. As you know, acoustic waves, the way you can think of it is like a guitar string. A string that is stretched between two things on a guitar. Okay. And when you pluck it, of course, it vibrates. Could do things like this. It will vibrate. And the amount it is displaced from the standard position, you could call that U. And this U is described by a differential equation of this form. Okay? And what is known is that usually on a string, you could have acoustic waves with any frequency. But the moment you pin it down at two ends, like in a guitar, it can only have certain resonant frequencies. As you know, a guitar, when you pluck it, it will give you very specific frequencies. And that's related to the length of this thing. You make it shorter, the pitch will go higher. Again, that's how you play a guitar, I suppose. You move along this. With your finger, you press it at different points. Okay. And all that you can understand starting from this equation. And let me quickly explain how you get this from this equation. Because in a way, of course, in this course is not about guitar strings. It's about this quantum guitar. It's about these electrons in a box. But the math is kind of similar. And you could use this to understand why electrons have discrete energies. That is, the same math that leads to acoustic waves having discrete frequencies makes electrons have discrete energies when you put an electron in a box. That is, when you pin it down, and which is kind of what a hydrogen atom does. You see, because whenever there's a positive charge, it pulls the electron in. It is kind of a box that keeps the electron in there. It's a complicated box, but basically it just confines the electron, just as the guitar string sort of confines the acoustic wave. Okay. So now let me try to explain from here the math that actually leads you to this expression for the frequency. So the first point is that when you have a differential equation like this, where the coefficients are constant, you can write the solution in the form of sines and cosines or exponentials. Exponentials meaning of the type e to the power minus I omega t, for example, or or you could write, so cosine omega t, sine omega t. So if we assume a solution of this form, now the nice thing about exponentials is when you take the second derivative of this, or rather the derivative of this with respect to time, it's equivalent to multiplying it by minus omega. That's the nice thing about exponentials. Taking derivatives is very easy. It's just like multiplying with that. See? So when you have this second derivative with respect to time, that really is like multiplying by minus omega twice. You see? And that is equal to v square d2u dz2. Okay. So this, of course, is minus. With the minus I, when you square it, you just get a negative sign. So it is minus omega square. And we can take the v squared from here, just divide it. And we get. Now, this equation, you could, again, now solve for the z dependence. And that is the idea that you have a differential equation whose coefficients are independent of z. It's constant. So actually, even the z part, I could write in the form of cosines and sines, or I could write in the form of e to the power plus ikz and minus ikz. Now, if I use this, then the nice thing about it is that this second derivative is like multiplying with ik twice. Or I could use sine kz, in which case, when I take the first derivative, I'll get k cosine kz, and when I take the second derivative, I'll get minus k squared sine kz. So again, the effect of taking two derivatives is like multiplying with minus k squared. And it's a little, you can see that either with exponentials or with sines and cosines, same thing. Anyway, so if it is sine kz, for example, instead of d2u dz2, I could just write minus k squared u. So this is one thing about differential equations I should mention, that, see, with algebraic equations, usually the way you solve it is, given a plus b equals c, you can say b is equal to c minus a. So by manipulating things, you can solve a set of algebraic equations. On the other hand, with differential equations, it's not quite like that. It's more like you write down a solution and see if it works. And over the years, people have tried out all kinds of things, and they have a nice catalog of things that work. And one of the things to remember out of that catalog is that whenever you have differential equations with constant coefficients, and by constant I mean what's here is independent of, say, time. In that case, the solution can be written in the form of an exponential in time, or cosines and sines. Or if it has something that's independent of z, then again you can write it in the form of exponentials, the solutions. Okay. So, and how do I know that's right? You see, if I hadn't known that, well, once you put it in, you can see that it will the solutions we have assumed will satisfy this equation, provided omega square over v square is equal to k square. So omega square is equal to v square times k square. So as long as omega and k are related by this relation, which is what's called the dispersion relation, something that in a later module we'll talk more about. So as long as omega and k are related this way, our assumed solution will satisfy this equation. Okay, so much for background then. Now remember the basic point I'm trying to explain is why when you take an acoustic wave, confine it, you get discrete frequencies. And the answer is that in order to fit into this string, you see, this U has to be at z equals 0, it must be 0, because you don't let it vibrate at that point. If you're fixing it, and you're fixed here, so at z equals L, it must be 0. So, if our solution has the form of sine kz, I can see that it will automatically be 0 at z equals 0. If I had used a cosine, it wouldn't work, so that tells me I shouldn't use a cosine, I should use a sine. That makes it 0, right? But then it also has to be 0 at that end. So what that tells me is that KL, sine, it's a sine KL must be equal to 0. So that tells me that KL must be equal to some integer times pi. So now what I have is, you see, previously K could have any value. And as long as omega was equal to V times K, I guess I should write that here just to remind you, omega equals Vk. As long as omega is equal to V times K, this solution would satisfy the equations. But now what we find is, as soon as we impose this boundary condition, any K is not allowed. K's must obey that relationship. Okay, so if K's must obey that relationship, it means the corresponding frequencies must obey a particular relationship, which you can see, well, for every n, let me put an n here to tell you that that's the K corresponding to a particular value of n. Okay, so similarly, the frequency is omega for a particular value of n is V times Kn, which is equal to n pi V divided by L. So that's it. I mean, these are then the allowed frequencies of a guitar string of length L. You make it shorter, the frequencies will go up. I mean, that's why the pitch goes up. Okay? Now, how do we apply that to the Schrodinger equation? A similar story, that if you, as I said, electron in a hydrogen atom is like an electron that's confined in a complicated box. Now, if you want the right quantitative answers for that complicated box, then of course you have to solve the complicated equation. And here, of course, we have a potential that depends on R, so we cannot just write down a solution as sines and cosines. Remember, that solution only works as long as these coefficients do not change with space. But what we could do is think of a simpler model problem. And let's do this in just one dimension. So we could write something like this. So in one dimension, you see E psi is equal to minus h bar square over 2m d2 dz2 psi. And for this discussion, we're putting the potential equal to 0. That means it is as if I have a box, you see, where the potential is 0, but then you say, well, then the electron is not confined, it will just go away. Okay, but assume that at the two ends, you got this huge potential barriers which keep it in there. Keep the electron inside this box. But then what I can do is I can solve this equation easily inside this box, where u is equal to 0, because now you see I have a differential equation with constant coefficients. I know how to write the solutions, I'll just write sine kz. That's it. And that should automatically satisfy that equation. And then what I'll do is I'll say, well, you got these big barriers, so the psi, which sort of gives me a measure of where the electron is, that should go to 0 at the two ends. This particular point, though, to do it properly needs a little more discussion. But let's assume then that what these barriers do is keeps the psi, makes the psi go to 0, just like what the guitar string, what this two ends kind of did to the guitar, made this displacement go to 0. So here also, it's like this wave function is forced to go to 0 at the two ends. Now, because it goes to 0 at the two ends, of course, we have the same story again. Math is the same. So again, now KNL is equal to n times pi. So this is exactly the same as the guitar. What is not the same is the next line, because the next line you can see with the guitar, omega was proportional to k. In this case, omega is not proportional to k. And you can see what it is. It's supposing for psi I put sine kz, then you see when I take the second derivative, as we discussed, with sine kz, when you take the second derivative, what you get is minus k squared times psi, the same thing. So instead of this, I could put minus k squared. So I could take this off, minus k squared, and I'll take off the minus. So now you can see E is equal to h bar square k square over 2m. So the point is, with the guitar, omega was proportional to k. With the electron, the energy is proportional to k square in this case. So it's h bar square over 2m and then times kn squared, which is like n squared pi squared over L square. And this is the answer you'll see. Again, if you look at any quantum mechanics text, they will usually start with this particle in a box problem. See, and one of the things you calculate is these energy levels of the electron in a box. But the main message I was trying to convey in all of this is this basic physical point that when you take a wave, no matter what wave, and put it in a box, that's when the allowed frequencies become discrete. And that is where we have a physical feeling, of course, for the acoustic wave, because the guitar we understand, it's got discrete frequencies, and you can change it, we understand that one. Here what we are doing is taking an electron wave, described by Schrodinger equation, and putting it in a box. And of course, when it's a hydrogen atom, it's a complicated box, not a simple one like this. But the basic physical thing you can see that if you put it in a box of some size, it will develop discrete energies, and these discrete energies, if you make this size of the box small, the energies will get further apart. Just like the guitar, make it shorter, the frequencies get higher. These will get, and if you make it long, the energies will get further apart. That's the physical thing I wanted to sort of stress here. And the one last thing, of course, is whenever people see the Schrodinger equation, they say, well, what is psi? Because when it came to the guitar, we have no problem explaining what is U. It's just the vibration of this thing. You know, how far the guitar goes up and down. It's easy. Here, what is psi? That actually took physicists many years to agree on exactly what it is. You know, what exactly we're talking about. Because roughly speaking, of course, psi is something that tells you where the electron is. That is, if psi looks like this, then this is a complex number. If you take its magnitude squared, which means if you multiply it by its complex conjugate, what you have will tell you roughly how the charge of the electron is distributed in there. So if it is peaked in the middle, that means the electron spends a lot of time around here and less at the two ends. And these are things, of course, these days people can measure using things like scanning tunneling probes, with which you can actually probe how the wave functions are actually distributed. But there are subtle conceptual issues which at this time I'm glossing over. And as I said, this is the point which took people many years to actually come to an understanding of what psi is. But one thing to note is that during all that period, while people were trying to figure out what psi means, no one had any doubt about the correctness of the equation. Why? Because the energy levels matched what you saw from experiment.